So in last segment we saw the derivation for the expression of velocity inside a circular pipe when the flow is laminar and steady. This video is part 2 of the Hagen-Poiseuille equation derivation.
So earlier what we saw was in shear stress, so shear stress tau is equals to minus dou p by dou x into r by 2. Here shear stress varies linearly with respect to radius. Here velocity varies with respect to square r square, which means it is not linear, it is parabolically changing. It is if tau linearly varies with respect to r, whereas u parabolically varies with respect to r. That profile is given here. See this, how velocity changes. See, with r, this being the maximum, this is the maximum value for v max or u max. This is the maximum value for shear stress tau naught. Maximum value occurs at what here? Tau. This is 1. This maximum value occurs at center. So velocity and shear stress, their maximum value varies. They won't be at the same point. For velocity, maximum value will be at center. For shear stress, it will be at the 1. Now, where will the maximum velocity be? At the center. At center, what is this value of small r? It is 0. Why? At center small r is equals to 0. Now we will apply this equation in the equation that we got there. U is equals to minus 1 by 4 mu into dou p by dou x into capital R square. This is maximum value of velocity. This is U max. This is U maximum velocity. Now we'll have a small relation now. We'll divide maximum velocity by normal value. What will we have? Minus 1 by 4 mu into dou p by dou x into capital R square by minus 1 by 4 mu into dou p by dou x into capital R square minus small r square. This goes. U max by u is equals to r square by r square minus r square. Here r capital R square. Now u max by u is equals to 1 by capital R square minus small r square by capital R square. I'm bringing this value down. Now what will happen? U max by u is equals to 1 by 1 minus small r by capital R whole square, which means what will we get? We'll take u here and this thing here. U is equals to u max into 1 minus small r by capital R whole square. This is another expression. This is, we'll express velocity in terms of the maximum velocity. Now we've derived the expression for velocity in terms of maximum velocity. Now let's go to discharge. See, discharge throughout the pipe. To find out discharge throughout the pipe, first we'll consider small element, same element that we've considered earlier for deriving velocity equation. We'll consider this same. This is an elemental cylinder inside the pipe. Here, what is the formula for discharge? dq, that is elemental discharge dq. We are not talking complete discharge will be q, complete discharge will be q, whereas elemental discharge will be dq. dq is equals to u dA. U is here velocity, or you can write it as v dA. What is the formula for v? That is what we have derived here. Formula for v is this one. We'll go here. we'll write that formula. Minus 1 by 4 mu into dou p by dou x into capital R square minus small r square into dA. What is dA? dA is the total area of this particular element. What is the total area? Total area is how much for where flow is happening. See, flow is going like this, which means it engulfs the whole circumference of the elemental area. Here, if we consider this, the whole circumference, there will be water flow, which means circumference into length of the elemental cylinder, that is the area. So what will come? Minus 1 by 4 mu into 2p by 2x into small r square, capital R square minus small r square into 2 pi r dr. This is dq. To find out q, what will we do? We should integrate the above equation, the limits being 0 to capital R. Why? Because 0 is at the center, capital R is the radius. We'll have q is equals to, we'll take out the constant. What are all the constants? 2 pi is constant, dou p by dou x is constant, and minus 1 by 4 is constant. We'll take that to the front. Minus 1 by 4 mu into 2 pi into dou p by dou x to integral 0 to r. What are the expression left? R capital R square minus small r square into r dr. Now we'll go slowly, we'll see how the derivation goes. Is equals to 2. So minus pi by 2 mu into dou p by dou x in integral of 0 to r limits capital R square r minus small r cube dr. What will come? Minus pi by 2 mu into 2p by 2x into r square into r square by 2 minus r power 4 by 4. This is the integration of this particular. When we integrate, we'll get this. We'll now apply the limits. Once we apply the limits, pi by 2 mu into 2p by 2x, we'll apply, see, once we apply 0, the whole expression will be 0, so we're not going to bother about that. Now we'll apply r square into capital R square by 2 minus r power 4 by 4 is equals to minus pi by 2 mu into 2p by 2x into r power 4 by 2 minus r power 4 by 4 is equals to minus pi by 2 mu to 2p by 2x into, what is this? What is the final value of this expression? R power 4 by 2 minus r power 4 by 4 is r power 4 by 4.
So the final expression for q will be minus pi by 8 mu into dou p by dou x into r power 4.
Since we got q, now we'll write q in terms of d. Here we have r. We are deriving the expression in terms of r. We'll write in terms of d. What is d? D is equals to 2r. So q is equals to pi by 8 mu into minus dou p by dou x into d by 2 whole power 4. That is q is equals to pi by 128 mu into minus dou p by dou x into t power 4. Why 128? You will calculate. 2 power 4 is 16. 16 into 8 is equals to 128. Now we have q here. What is the area? Area of flow is, pipe is pi r square. Now we have q and we have area. To find out, we can, if we divide this q, this value of discharge with this area, we'll have mean velocity, that is velocity on an average value. Whatever we are deriving there, minus 1 by 4 mu into r square minus r square, they are all instantaneous velocity at particular radius. Now what we'll be seeing is mean velocity for the entire pipe. How much is the velocity that can be averaged? Now v mean is equals to q by a. We'll substitute this pi by 128 mu into minus 2p by 2x into t power 4. In terms of this, pi by 4 t square, pi by 432 t square square. So v mean is equals to 1 by 32 mu into minus dou p by dou x t square. This is v mean. What is v max that we got earlier? What is the value of v max? 1 by 4 mu into minus dou p by dou x into capital R square. What is capital R? Capital R square is equals to t square by 4. Okay, so t square by 4, that is 1 by 16 mu into minus dou p by dou x into t square. This is v max. We divide these both expressions, v mean and v max. What will we get? V mean by v max is equals to, what will we get? All these expressions, dou p by dou x will get cancelled, mu will get cancelled, 16 here it goes by 2, d square cancel. V mean by v max is equals to 1 by 2, that is v mean is equals to 1 by 2 v max. Now we got this expression between v mean and v max. We've already derived an expression for v in terms of v max, that is v is equals to v max into 1 minus small r by capital R whole square. Now if we equate these two equations, we'll find out at what radius, that is at what r v will be equals to v mean. It is at what value we'll get the mean velocity, at what radius value we'll get the mean velocity. Now we'll equate these two. Now from here, what is v max? V max is equals to v by 1 minus r by capital R whole square. We'll substitute this in that. We'll substitute this in this equation. Now v mean is equals to 1 by 2 into v by 1 minus small r by capital R whole square. To find out what is this value of small r, we should assume that this value, this v value is equals to v mean. And we are finding out at what value of r v is equals to v mean, which means v is v mean here. We'll write this as v mean only. Now what, these both will get cancelled. Now it implies 1 minus small r by capital R whole square is equals to 1 by 2. Small r by capital R whole square is equals to 1 by 2. Small r by capital R is equals to 1 by root 2. Small r is equals to capital R by root 2. In terms of numerical values, what will we get? Small r is equals to 0.707 capital R. So this is the value of the radius at which v is equals to v mean. That is, if we say the problem or if anything is given as such, so they give you a discharge, they give you area. You find out velocity by calculating q by a, you'll get v mean velocity. this v mean velocity will happen at a point of this much distance from the center. It is from the center. If we take this pipe from the center, if you take 0.707 r, that is where you'll get the average velocity value.
Now, what is the value of v? We'll go back to the expression of v mean. What is the expression of v mean? V mean is equals to minus 1 by 32 mu to 2p by 2x into t square. In terms of d, we are dealing. This is t. Now, from this 2p by 2x, p by 2x is equals to 32 mu v mean by t square minus 32, or we'll take minus over here. We'll put minus 2p by 2x only. From now onwards, we'll call v mean as v only. So the expression will become 32 mu v by t square. What is 2p by 2x? That is change of pressure with respect to length. What is change of pressure here? Minus P2 by P1. Say if you are taking 2 points, the change of pressure between those 2 points will be P2 by P1. What is change of pressure? What is change of length? Nothing. If you take from starting of the pipe to ending of the pipe, del x is equals to L, that is length. X is length, is equals to 32 mu v by t square. From this, what will we get? Minus we'll take inside, so P1 minus P2 is equals to 32 mu VL by T square. Now here we can take V as Q by A. V is average velocity is equals to discharge by area. So 32 mu into Q by A to L by T square. Since area will now come down, what is area? Area is equals to pi by 4 d square. We'll multiply that with d square. What will happen? 32 mu q L by pi by 4 into t power 4. T square already here, from area another t square. So P1 minus P2, the final expression will be 4 will come on top, 128 mu ql by pi d power 4. See, these both expressions these both expressions are called Hagen Poiseuille equation. So at last we have derived this Hagen Poiseuille equation. Hagen Poiseuille equation is relation between pressure difference and velocity, length, discharge and area. So amalgamation of the pressure, viscosity, velocity, length, diameter. So finally we have derived the Hagen Poiseuille equation. There are a few more other relations that we can derive from this. See, we know HF, that is head loss due to friction, is equals to P1 minus P2 by rho g. We got the expression for P1 minus P2 over here. We'll use that here. So HF is equals to 32 mu VL by rho g t square. Now we'll segregate terms here. I'll segregate it for you. We can write this as 32 L by rho v t by mu.
Here since there is V, finally you should get V, we'll write V square. There's already D, we'll write another D. Have that is 32 LV square by rho VD by mu. Mu will again come over there, there is rho, there is G into G. This can be written as 64 LV square by rho VD by mu into 2GD. See, once you solve this equation, you'll get 2 here goes 32, VV goes, then mu will come on top. Final equation will come as 32 mu VL by rho GD square only. But we are making the equation a different way. So from this you can see where we are heading. This is 64 by, what is rho VD by mu? Reynolds number. 64 by RE into LV square by 2GD. This is the expression for HF, head loss due to friction. We'll mark this separately. Okay. Now, you already seen the expression for head loss due to friction. What is it? HF is equals to FLV square by 2GD. We'll equate this here. Okay, we'll equate this. What will happen? FLV square by 2GD is equals to 64 by RE into LV square by 2GD. See, all this L is same, V square gets cancelled, 2GD, everything, which means finally we get friction factor F is equals to 64 by RE. This is the friction factor for laminar flow in a circular pipe. Okay. If you might remember, when dealing with the loss of fluid friction, I told you that in laminar flow the friction doesn't depend on the nature of the surface. That is, whatever may be the nature of the surface, the friction doesn't depend on it. Here F is an indication of friction. See, what is the value of friction? 64 by RE. 64 is constant. What is the formula for RE? RE is equals to rho VD by mu. Here rho is density of fluid, D is velocity of fluid, D is diameter of the pipe, mu is viscosity of fluid. There is no indication of what the surface roughness or how, whether if it is a cast iron material, whether if it is a PVC, it doesn't matter. For laminar flow, friction only depends on Reynolds number, that is rho VD by mu. That's it. There is no indication, there is no necessary for you to consider what sort of a material that pipe is made of. This is what we discussed at that point. That point I told you that I'll tell you why. Now we derived an expression here. We derived an expression proving that yes, in laminar flow, friction will not be dependent on the nature of the surface.
So that concludes our topic, Hagen-Poiseuille equation. I know this topic is a bit big and bit difficult, but this is equally important. Now, after this, the next topic will be flow between parallel plates. Now we saw flow inside a pipe. Next thing will be two parallel plates and flow between them. We'll see that in the next segment. Thank you.